Okay, class. Okay, we are now in our last part of chapter 4. Okay, still on frequency response, but on filters types. Okay, so as introduction, so a filter is a circuit that designed to pass signals with a desired frequency and also reject or attenuate others. Okay, so passive resistors consists of only passive element R, L, and C. Okay, so there are four types of filters, which get classified as low pass, high pass, band pass, and band stop. Okay, so ideally frequency response omega of the four types of these filters, the low pass, is designed to pass only frequency, from DC up to the cutoff frequency. This frequency, only pass the signals in between 0 to omega c. For the high pass, is designed to pass all frequency above the cutoff frequency omega c. So it's allow only the frequency above the omega c or the cutoff frequency. The band pass is designed to pass all frequency within a band of frequency from omega 1 to omega 2. So they designed to pass the frequency in between the omega 1 and omega 2 here. And the band stop is designed to stop or eliminate all frequency within the band of frequency, which are from omega 1 to omega 2. So it will eliminate the frequency in between omega 1 and omega 2 and passes all the frequency beyond this omega 1 and omega 2 and upper of omega 2. All right. Okay, so we have two types of filters. The passive filters consists of only passive RL and C. The active filters consists of the active elements such as transistor, op-amp, etc. In addition of passive elements. The passive low pass filter. So the R and C. The passive we can design from the RC series circuits. So from here, your magnitude is equal to V out divided by V in. The capacitor is your the voltage across the capacitor is your V out is 1 over J omega C times V of I. And your V in is the summation of VR plus V of VC. So your I times V of R plus 1 over J omega C. And now we do the cross multiplication at the denominator of it. Denominator side. And then here we get your above, sorry, your below or denominator is 1 after doing the cross multiplication, 1 plus J omega RC, and then you bring the J omega RC up, and then the numerator you will get 1. And then to get the cutoff frequency of the roll-off frequency omega c, the magnitude is equivalent to 1 over square root of 2. At this frequency, if you assume your Z is equivalent to square root of R. So 1 over this the omega c squared R squared and plus with 1 squared is equivalent to 1 over square root 2. So finally, your omega c is 1 over RC. So the low pass filter can be also performed when the output of LS circuit is taken off the capacitor. So at this time, for the low pass, when your omega is equal to 0, so you put here your omega is equal to 0, your magnitude is equal to 1. When your omega is equal to infinity, 1 divided by infinity, so you will get the magnitude is 0. So, you have this curve, the actual curve, when you have 0 is 1, and when you have the infinity is 0. And then this is when, your H omega or your magnitude is equal to 1 over square root of 2 is 0.707. Is here at omega c. Okay, so omega c is 0.707, right? So this is the low pass, which is pass only the signal in between 0 to omega c. Alright, for the passive high pass filter, so you have the R and C in series, but your V out is now your V out the voltage across your resistor. And then from here, V out divided by V in, is your R divided by R plus 1 over J omega C. You do the multiplication, the R times with your J omega C, and you left your 1 here, and then you bring your J omega C, outside, and then you will get, the J omega C RC divided by 1 plus with J omega C RC. So from here also you put, your critical point at omega is equal to 0. So you will get from here, when omega is equal to 0, so you will get your magnitude equal to 0. Because 0 divided by something is 0. So here when your omega is equal to infinity, you put your infinity, infinity divided by infinity, so your magnitude will give you 1. So this is 0. When omega is equal to 0, you get 0. When your omega is equal to infinity, you get your h is 1. So this is the actual curve, but ideally, so this is the curve. And this is where your omega c is equal to 1 over RC, or is equivalent to 1 over square root of 2. This is 0.707. So for the high pass filter, we know that the filter is designed to pass the frequency that over of the cutoff frequency. So the passive band pass, the passive band pass is when your R, L, and C are in series, and your V out is from your the voltage across your resistor. So your V out divided by V in, so your R divided by the total of the voltage across your inductor, capacitor, and resistor. So you have the R divided by R plus J omega L minus 1 over J omega C. So for the cutoff frequency, the omega naught is equal to 1 over square root of LC. And then this is your, you can put, you can take the critical points at omega is equal to 0. So when you put omega is equal to 0, so you have this h is equal to 0. When you put your h is equal to infinity, sorry, your omega is equal to infinity, so you put infinity here, divided by 1 something equal to infinity, so you also have your magnitude is equal to 0. You can try substitute it. Finally you will get, you should have this magnitude at these 2 points will give you the magnitude at 0. So you have 0 for your omega at 0, and omega at infinity also 0. So you have this curve. For your omega is equal to naught, omega naught, so you have 1 over square root of C. And between this omega 1 and omega 2, the magnitude is 0.707, or 1 over square root of 2. So this is your actual curve, and this is your ideal curve. And we know that your band pass is allow the frequency in between your cutoff frequency, or in between your omega 1 and omega 2. The halfway frequency, bandwidth, and quality factor can be calculated using the formula in series resonance, because they are in series resonance for the band pass filter. Alright, so the passive band pass, band reject or Knox filter or RSC. Okay, so now your VR, okay, is determined from your output at your voltage across your capacitor and inductor will be your VR. Okay, so you have the transfer function is J omega L minus 1 over omega C. Okay, divided by the total of all these voltage drop across the resistor, capacitor, and inductor. Okay, so R plus J omega L minus 1 over omega C. Okay, and the cutoff frequency also omega naught is equal to 1 over square root of LC. Okay, and then you put the omega at 0. Okay, so you have the H equal to 1. When you put your H is equal to infinity here, okay, you replace the omega with infinity, so you get your H is equal to 1. So you have 0, 1, you get the magnitude is 1. Okay, the infinity also you get there. Okay, the value of the magnitude is also 1. Okay, and then the omega 1 and omega 2, okay, the magnitude is 1 over square root of 2, which is 0.707. Okay, so this is the actual curve, and this is the ideal curve. Okay, so for the band stop, okay, it means eliminate, okay, or stop all the frequency in between omega 1 and omega 2. Okay, it's allow, okay, the frequency below the omega 1 and the upper of omega 2. Okay, for the quality factor, halfway frequency and bandwidth, okay, you can use the series resonance circuits because they are, okay, the RL and C are configured, okay, in series, okay. So the omega naught is a frequency of rejection and the B is a bandwidth of rejection.